So as I said, our speaker is Andrew Suk, and he'll talk on cliques and sunflowers under bounded VC dimension.
Okay, so thank you for inviting me to speak in this seminar. So I'll be talking about cliques and sunflowers under bounded VC dimension. This talk is about two projects, both of which are joint works with Jacob Fox and Janos Pach. And the first half of this talk will be about graphs with bounded VC dimension. And just to be thorough, I'll start off with the definition of VC dimension. So given a set system F with a ground set V, we say that a subset S of your vertices is shattered by F if for every subset of S, you can find a set A in your family that contains exactly those members from S. And so the VC dimension of this family F here is simply defined to be the size of the largest subset of vertices that can be shattered by F. So when I talk about the VC dimension of a graph, what I mean is the following. So let G be a graph. Then for each vertex, I can look at the neighborhood of that vertex, which is a subset of the vertices. And I'll denote this neighborhood with this N of V here. And if I collect all of these neighborhoods generated by each vertex, I get this set system F here. And I'll often refer to this set system as the neighborhood set system. So in particular, this neighborhood set system, it has n vertices and exactly n sets, possibly with multiplicity. And so we define the VC dimension of this graph G here to be simply the VC dimension of its neighborhood set system. So I'll be focusing on graphs with bounded VC dimension. I come from, I guess, a combinatorial geometry background, and graphs with bounded VC dimension often pop up in the problems that I see. So just to give you some examples of graphs with bounded VC dimension, the intersection graph of segments in the plane, these graphs have bounded VC dimension. The unit distance graph of points in RD, where D is fixed, these graphs also have bounded VC dimension. And these two examples here, they're actually examples of what are known as semi-algebraic graphs. So a semi-algebraic graph is a graph where your vertices are points in RD, and your entire edge set can be defined with just a constant number of polynomial equations and inequalities. And it's known that semi-algebraic graphs with bounded complexity, it's known that these graphs have bounded VC dimension. And of course, there are interesting graphs that are not semi-algebraic, but still have bounded VC dimension. And one nice example would be the intersection graph of pseudo-segments in the plane. So pseudo-segments is just a bunch of curves in the plane such that any two curves have at most one point in common. So one general question that me and my co-authors have been thinking about the past several years is whether or not we can substantially improve some of the classical theorems in extremal graph theory for graphs with bounded VC dimension. So just to give you some examples, here are three classical theorems from extremal graph theory. And it's known that in the semi-algebraic setting, so if we add this extra condition that our graph is semi-algebraic with bounded complexity, then it's known that we can significantly improve all of these three results here. And so then you might wonder whether or not you can extend these improvements to graphs with bounded VC dimension. But if you think about this problem just for a little bit, you'll quickly realize that this might not be so easy. One problem you'll see is just the sheer number of such graphs. So what I'm saying is that it's known that the number of semi-algebraic graphs on n vertices with bounded complexity, this number is roughly 2 to the n log n. So in particular, the class of semi-algebraic graphs, it's a rather small class of graphs, whereas the number of n vertex graphs with bounded VC dimension, this is actually much closer to 2 to the n squared. And it's actually not so difficult to see that actually one of the theorems that I stated earlier, there wouldn't be any improvements in the bounded VC dimension setting. So it's known that every K22 free graph on n vertices has at most n to the 3/2 edges. And if we add this extra condition that this graph kind of arises naturally in geometry, so it's semi-algebraic with bounded complexity, we know that we can significantly improve this upper bound to this quantity here. But if your graph is K22 free, then it already has bounded VC dimension. And so therefore, the bounded VC dimension setting, it doesn't help your situation. And it's known that there are K22 free graphs on n vertices with at least n to the 3/2 edges. So here, there wouldn't be any improvement. So the first main result that I like to talk about here today is in joint work with Jacob Fox and Janos Pach, where we established type bounds for multicolor Ramsey numbers for graphs with bounded VC dimension. So multicolor Ramsey numbers are pretty well studied. And so I'll start off with its definition. So it's this thing here, this R3333, where there's m of these threes. So this thing here is the minimum integer n, such that for any m coloring of the edges of the complete graph on n vertices, somewhere there's a monochromatic copy of K3. So this is a pretty well-studied function. So when m is 2, we know that R33 is equal to 6. And when m equals 3, this thing equals to 17. When we have 4 colors, it's somewhere between 51 and 62. And then for 5 colors, we have these upper and lower bounds here. And for general m colors, it's not hard to see that it's at least 2 to the m and at most m factorial. The lower bound of 2 to the m can be seen as follows. So you just take the complete graph on 2 to the m minus 1 vertices and inductively color all of the edges with m minus 1 colors, such that you don't produce a monochromatic triangle. And then you take another copy of that thing. And then for all edges going across these two parts, you give it the mth color. And then this coloring would show that, well, it would give this lower bound of 2 to the m for this multicolor Ramsey number. The upper bound can be seen essentially by pigeonhole and by induction. So it's this arguments where you just pick any vertex, you look at all of the edges emanating out of it. By pigeonhole, if every edge has one of m colors, there must be a color that appears at least n over m times. And then if you look at that neighborhood, if there's a red edge here, you would have your monochromatic triangle. Otherwise, there's at most m minus 1 distinct colors inside. And so therefore you can apply induction, and this would give your m factorial upper bound. Okay. So as of today, I believe these are currently the best known upper and lower bounds for this multicolor Ramsey number. The lower bound can be seen by combining two results, one due to Frederickson and Sweet, and another one due to Abbott and Moser, which gives this lower bound of 3.199 to the m. And the best known upper bound is that argument that I just gave of m factorial, which I'll simply write as 2 to the m log m. And so it's conjectured that you can significantly improve this upper bound of 2 to the m log m to 2 to the constant times m. And this conjecture is still open. And several years ago, me and my co-authors were able to verify this conjecture if the color classes were semi-algebraic with bounded complexity. So kind of the colorings arise naturally in geometry. And then about a year ago, we were able to extend these results to colorings with bounded VC dimension. So before I can state this a little bit more precisely, I need one more definition. So suppose we have the complete graph on n vertices, and every edge is colored with one of m colors. Then if I fix any vertex, I can look at the neighborhoods with respect to each color class. So I can look at all of these neighborhoods. And I'll denote n sub iv to be the neighborhood of v with respect to the ith color class. And then if I collect all of these neighborhoods, and then if I do this for every vertex, I again get this neighborhood set system F here. And if we assume that this neighborhood set system F here has bounded VC dimension, then what we were able to show is that this multicolor Ramsey number is at most 2 to the constant times m. So we were able to show it's at most 2 to the constant times m, and you can see that it's at least 2 to the constant times m by that simple bipartite construction that I just mentioned earlier. So the construction that I just mentioned earlier, it's not hard to see that that has bounded VC dimension. So that shows that this is indeed on the order of 2 to the m. Okay, and there wasn't anything special about the number 3. So, so for any fixed constant p, if you want to obtain a monochromatic clique of size p and an m coloring of the edges of the complete graph, we were able to show that this is also indeed at most 2 to the constant times m. Okay. So what I would like to do now is I'd like to sketch a proof of this upper bound here. Just a sketch. So I'd like to sketch a proof showing that if you do have a complete graph on n vertices where n is this quantity here, so 2 to the constant times m, where c is a sufficiently large constant, and if every edge has one of m colors, and we assume that this neighborhood set system has bounded VC dimension, then I want to argue that somewhere there's a monochromatic triangle. Okay, so the idea of the proof, or at least the goal of the proof.
There is a question about constants in the chat. Okay, so that's for the previous slide, I guess.
This one?
Well, Matko, maybe could I ask you to unmute yourself and explain the
yeah,
question?
sorry, I didn't. Yeah, I saw something pop up, but let me see. How does the constant in the exponent depend on p? So I believe it's exponential in p. So it's hold on, how do I go back? So I believe, so exponential in p in the exponent, I believe. Hold on, there's another. Okay, thanks. Okay, any other questions? Okay, So suppose we have this M coloring of the edges of this complete graph on 2 to the constant times M vertices. So we want to find a monochromatic triangle. So the goal of the proof, and what would be nice, is if I can find a vertex such that with respect to one of the color classes, it has a very large neighborhood. And when I say large, I mean an absolute constant times n. So like n over 100 or something. So if this were true, then this would be nice, because that would be done, because either I have a red edge here, in which case I have my monochromatic triangle. Otherwise, there's at most m-1 distinct colors inside of here. And if this neighborhood is big, it'll be bigger than this quantity here if C is big. And so since it's bigger than this quantity here, I can just apply induction to find my monochromatic triangle inside of this neighborhood. So if I can find a vertex with very, very large degree with respect to one of the color classes, I would be done. But unfortunately, this isn't true. There's no reason why this would be true, at least at the beginning. And the only thing you can conclude at the beginning is that, there's a vertex by pigeonhole with such that with respect to one of the color classes, it has at least n over m neighbors. So in order to kind of improve the situation, what we do is we apply a partition theorem on the vertex set that gives us some structure of our colorings. But before I can state this lemma, I need one definition. So remember, we have this neighborhood set system F here. Now, two vertices in my ground set, U and V. A set A crosses that pair of a set A crosses that pair of vertices if it contains exactly one of the two vertices. So I guess in this example, the set A here crosses the pair UV because it contains U, but it doesn't contain V. And so, so this here is this partition lemma, which I should say is almost a direct application of the Hausler-Packing lemma. So remember, we have this neighborhood set system F here with bounded VC dimension. And this lemma says that for any delta between 1 and F, you can equipartition your vertex set into R parts where R is not going to be too big, such that for any pair of parts in the same part, for any pair of vertices in the same part, like these two red vertices here, very few sets from my set system will cross that pair of vertices. So at most 2 times delta sets will cross any pair of vertices that lie in a single part. I should mention that this equipartition part, this actually isn't true, but for sake of presentation, we can just assume that it's true. So now that we have this partition lemma, we can make this really nice observation, which is that if I look at any of the parts, let's say this part here, and if there's a red edge inside of there, then I can assume that every vertex inside of that part has a small degree with respect to that same color class. So I guess red in this example. Because if there was a vertex in that same part with large degree with respect to the red color class, I would be done. I would have a monochromatic triangle. And so in order to see this, suppose this vertex here has very large degree with respect to the red color class. Then if I look at any of its neighbors, let's say V here, and if I look at the red neighborhood of V, well, since this edge is red, the red neighborhood of V must contain this vertex. And if it doesn't contain both X and Y, the red neighborhood must cross either one of these two black edges here, or both. So if the red neighborhood doesn't contain both X and Y, it would cross at least one of these two black edges. And I know that there are few sets in my set system that crosses either one of these two black edges. So therefore, if this neighborhood is sufficiently large, eventually there must be a vertex U such that its red neighborhood doesn't cross either one of these two black edges. But the only way that can happen is if the red neighborhood contains all three of these vertices. And if that happens, that means UX is red, UY is red, and since we assumed XY is red, this gives us our monochromatic triangle. So therefore, anytime, so either I'm done, either I found my monochromatic triangle, otherwise I can assume that anytime a color appears inside of a part, every vertex in that part has small degree with respect to that color class. Okay, and so now I can break up my proof into two cases. The first case is when one of the parts has very few distinct colors. So for example, let's say this part, there's not many distinct colors appear. Well, since it was an equipartition, the size of this part will be pretty large. And since there's few colors, I can basically apply induction and find my monochromatic triangle that way. So if we're in case one, we're done. Otherwise, we can assume that every single part has many distinct colors appearing inside of there. But remember what that means. That means every vertex has many small neighborhoods with respect to those color classes. So I can assume that now each vertex has many small neighborhoods with respect to many color classes. But remember, there's n-1 neighbors because all of the edges are colored, which means that these color classes here must be bigger or bigger than the average because these will be smaller than the average. And so as you can see what just happened, remember at the beginning, the only thing we could have concluded was pigeonhole. So at the beginning, the only thing we were able to say is that these neighborhoods had size n over m, which was the average. But since we applied the partition theorem and since we ruled out case one, we can actually now conclude that actually each vertex has many small neighborhoods, which means that these neighborhoods are actually bigger than the average. And so now what you can do is you can basically iterate this argument. And after you iterate this argument, either you found your monochromatic triangle, or you can conclude that actually there's even more smaller neighborhoods with respect to each vertex. And that means that these neighborhoods down here are actually even larger. And so basically you can just keep iterating this argument and after roughly log star n times, you'll be able to conclude that these large neighborhoods here actually have size constant times n.
What are these down neighborhoods? I think I'm a bit lost there.
Sorry?
So can you repeat this part? Like, what are the neighborhoods that you have larger?
So with respect to each color class, I mean. So this is like the neighborhood with respect to the red color class. And this is the neighborhood with respect to the blue color. So with respect to each of the M color classes. And before we said that anytime a color appears, that means those neighborhoods must be small. And we assume since we're in case two, since there's many distinct colors, like red, blue, green, purple, or whatever, since there's many distinct colors in every part, every vertex has many small neighborhoods with respect to those color classes that appeared in the part. Which means, but you know, every edge is colored. There's n-1 neighbors. And so that means these neighborhoods would be bigger, or at least bigger than the average, because these will be smaller than the average. So for example, at the beginning, since there's m colors, you know, we assume that each neighborhood had size n over m. But because of the situation we were in, actually these neighborhoods were smaller, which means that these neighborhoods must be bigger because there's n vertices in total.
Yeah, makes sense. And how did you rule out the case? How did you get into case 2? So if you have few, if you have this case.
So if one part had few colors, so I assume it's an equipartition. So the parts are pretty large, basically. And if one of the parts only had like 2 colors inside, then we would just be done by induction. So we ruled out case 1 by induction.
Okay.
And then so therefore we can assume that all the parts had many colors, which gives us this situation.
Thank you. Thanks.
Okay, so after you iterate this argument over and over, you know, either you win, you found your monochromatic triangle, or you can conclude that there's lots of small parts, lots of small neighborhoods with respect to many color classes. And then this large color class down here would be of size constant times n. And then remember, that was our goal. If we found a vertex with very, very large degree with respect to one of the color classes, we would be done by induction. So I didn't go over the calculations, but I would say most of the key ideas of the proof were presented. Are there any other questions about that argument?
I guess I had a question, which is, what are you iterating on? I guess the equipartition lemma depended, like I guess what small or large means depends on.
Yeah, so you iterate, okay, so I guess in more detail, let me see. So here's where I claim you just iterate. So this partition lemma required this neighborhood set system, and then you do this partitioning. You can basically get rid of these. So the technical analysis, you actually get rid of these edges, and then you just take these large neighborhoods, and so your set system becomes smaller. There's fewer sets, and when you have a smaller set system, the partition lemma becomes stronger. And then you do it again, you're in a better situation because you have fewer neighborhoods to worry about. And then after you iterate again, you have even smaller set system. And so therefore you have a stronger partition theorem, and et cetera, et cetera.
Thank you.
Okay, any other questions? Okay, so this is what we just discussed, or kind of gave a sketch proof of. This upper bound on the multicolor Ramsey number, if we assume the neighborhood set system has bounded VC dimension. So the general upper bound of 2 to the m log m, I'm not aware of any other classes of graphs that can significantly improve this upper bound of 2 to the m log m, other than graphs with bounded VC dimension. And actually, one more class of graphs, which is, I guess, the intersection graphs of sets of size m. So what I'm saying is the following. Suppose we have a collection of sets of size m. So we have this m uniform family. And then I take the complete graph where my vertices are these sets, and I color each edge, which is a pair of sets. I color it with color I if they have I vertices in common, those two sets. And so therefore you can ask, how large does this family have to be in order to guarantee a monochromatic triangle in this complete graph? And by sure, we know that if we have 2 to the m log m of these sets of size m, we would have a monochromatic triangle. But there was a recent breakthrough due to Alewies, Levitt, Wu, and Zhang that actually said that the size of your set system can be much smaller in order to guarantee a monochromatic triangle. So they show that if the size of F has size 2 to the m log m, then that's enough to force this monochromatic triangle. And of course, what they proved was something much stronger, which is something about sunflowers, which I'll now talk about next. Okay. So now I'll be talking about these things called sunflowers. So the situation is that you have this F, the set system F that's M uniform. So every set has M vertices. And P sets, A1 through AP, form a P sunflower if their pairwise intersections are exactly the same. Just for simplicity, I'll just focus on the 3 case. So this is when things start to become interesting. 2 sunflowers are trivial because any 2 sets form a 2 sunflower. And likewise, one sunflowers are also trivial. So I guess this is a picture of a 3 sunflower. So if I pick any 2 sets, they intersect exactly on this vertex here. And this intersection here is often called the core, and then these things out here, the set minus the core, they're often called the petals. And I should note that 3 pairwise disjoint sets is a 3 sunflower because they pairwise intersect on exactly the empty set. And so the famous theorem of Erdos-Rado states that if you do have this M uniform family, this set system here where every set has size M, and if it doesn't contain a 3 sunflower, then the size of your family is m factorial times 2 to the m. So basically, again, 2 to the m log m. The proof is pretty simple, and I'll kind of use the argument later. So I thought that I would just quickly present the proof of this upper bound. So the proof is as follows. We know there's no 3 pairwise disjoint sets because that's a 3 sunflower. So we can just assume that there's 2 disjoint sets. And if not, our situation would be even better. So if I'm looking at these 2 disjoint sets, each set has m vertices inside. So I'm basically looking at 2 m vertices. And these 2 m vertices will hit every set in my family because there's no 3 pairwise disjoint sets. So these 2 m vertices hit every set in my family. And so therefore, by pigeonhole, one of those vertices will contain at least this many, will hit at least this many sets from my family. And so now if I look at those sets, let's say these red sets that contain this single vertex here, I can modify those sets by pulling that vertex out and getting a bunch of sets of size m minus 1. And the key observation here is that if there's a 3 sunflower there, that would correspond to a 3 sunflower in the original set system. So basically I can apply induction now, and that's exactly how you get this m factorial times 2 to the m quantity here. Okay, so I think there are several lower bounds, but I think this is maybe the most popular one. So you can get a lower bound of 2 to the m by taking m parts. Each part has 2 vertices inside, and then you take all sets of size m by selecting 1 point from each part. Then we would have 2 to the m sets, and it's not hard to see there's no 3 sunflower because remember the petals need to be pairwise disjoint, and there's only 2 vertices inside each part. Okay, so the famous Erdos-Rado conjecture states that you can significantly improve this upper bound of 2 to the m log m to 2 to the constant times m. And over the past several decades, there have been several improvements on this upper bound. But the recent breakthrough that I mentioned earlier due to Alewies, Levitt, Wu, and Zhang showed that the size of such a family is at most 2 to the m log m. And as of today, I believe this is currently the best known upper bound for this sunflower problem. Okay, and so what me and my co-authors were thinking about this past year is what would happen to this sunflower problem if our set system was defined geometrically. So for example, what if the set system was defined by points and disks in the plane? Or more generally, what if our set system had bounded VC dimension? So the first thing I guess you would want to see is whether or not this significantly changes the problem by adding this extra condition of having bounded VC dimension. If you go back to that example we were just talking about, it's not hard to see that this example has large VC dimension. So this isn't a good example for the bounded VC dimension setting. But it's also not hard to come up with an exponential lower bound in this bounded VC dimension setting. So if you just take the binary tree of height m, and then you take all root to leaf paths as your sets of size m, you will generate 2 to the m minus 1 sets of size m. And this set system will have VC dimension 1. And again, there wouldn't be a 3 sunflower. So even in the bounded VC dimension setting, the lower bound doesn't really change much. And you can even realize this tree thing geometrically. So what I'm saying is you can even realize this set system with points and disks in the plane. And I believe you can even do it with points and half spaces. So your vertices are points, and then your sets are certain half spaces that contain exactly m of those points. So even in the semi-algebraic setting, the lower bound doesn't really change much. Okay, and so the second main result that I wanted to talk about here today is this result here, which is again joint work with Jacob Fox and Janos Pach, where we gave a new upper bound on the sunflower problem if we assume that f has bounded VC dimension. So again, if f is an m uniform set system with bounded VC dimension and no 3 sunflower, we show that the size of the family is at most 2 to the m log star m. And so now what I like to do in the last 10 minutes of my talk is to sketch a proof of this upper bound here. The proof is essentially by induction on M, the uniformity. So suppose F is this M uniform set system with bounded VC dimension and no 3 sunflower. We want to show that it's at most this quantity here, which is kind of ugly, so I'll just call it FD of M. And so we want to show that the size of F is at most this FD of M quantity here. And so for sake of contradiction, suppose the size of the family is bigger than that quantity that we claimed. So we have this set system with all of these properties, bounded VC dimension and no 3 sunflower. So what we'll do first is we'll set little s to be this number here, which let me just say is super polynomial in M. And then we collect the S highest degree vertices. So we collect the S most popular vertices with respect to degree, and then we call those set of vertices capital S. Now that I've collected the S highest degree vertices over here, I can conclude that every vertex outside of S has a degree at most this quantity over here. And this can be seen just by double counting, because we know if we sum up the degrees of every vertex in our set system, since it's M uniform, it's exactly M times the number of sets. And so therefore, if I just sum up the degrees of the vertices inside of S, that'll be at most M times the size of F. And since the vertex here, the degree is at most the degree of all of these vertices here, we get this inequality here. And then if I just cross multiply the S, I get this upper bound on the degree of this vertex U here. And let me just reiterate that S is super polynomial in M. So this M over S factor, it's tending to 0 as M tends to infinity. Okay, so since every vertex outside of S has small degree, if I look at any set A, it might contain some vertices in S and some vertices outside of S. But since these vertices have small degree, I can conclude that A intersects very few other sets outside of S. Which means that I can conclude that there are many triples in my set system that are pairwise disjoint outside of S. And remember, just because I have a triple of sets that are pairwise disjoint outside of S, that doesn't necessarily mean they are a three sunflower, because remember, I have no idea how they behave inside of S. It's possible that the three sets lie completely inside of S, and so therefore I would have no idea how they behave. Okay, so now we can break up the proof into two cases. The first case is when at least half of the sets intersect S in a rather small way. So on just log M vertices. So suppose many sets intersect S on just log M vertices. And if I just look at those sets, and then I look at the intersection between those sets and S, I get these little sets of size at most log M. And if I collect all of those sets, I can get this set system F prime here. So this set system F prime, it's on S, and every set is very small. Every set has size at most log M. A couple of more things about F prime. It could be a multi-set system, because it's possible that two sets intersect S exactly the same way. And also by assumption, F prime is very, very large, or it's at least this big. So basically now I'm going to kind of cheat. But before I do that, let me just say that if you think about the sunflower for multi-set systems, so if you allow sets to repeat, this doesn't really change the sunflower problem much. Because remember, if a set repeated 3 times, that's a 3 sunflower, because they pairwise intersect exactly the same way. So allowing sets to repeat doesn't really change the sunflower problem much. And also, instead of having sets of size exactly log M, you have sets of size at most log M. This also doesn't really change the sunflower problem much. So with that in mind, essentially by induction, since F prime is so large, it has size essentially 2 to the M log star M. The sizes of the sets are very small. They only have size log M. Essentially by induction and like a crossing lemma type argument, you can conclude that F prime has many triples that form a 3 sunflower. And since F prime was large, that means that you can actually conclude that there are many triples in my original family that forms a 3 sunflower inside of S. And so therefore, what we just concluded is that there are at least this many triples that form a 3 sunflower inside of S. Pretty much all of the triples are pairwise disjoint outside of S. And if you work out the numbers, you can basically apply pigeonhole at this point to conclude that there must be a triple of sets that are pairwise disjoint outside of S and form a 3 sunflower inside of S, which means that they would form a 3 sunflower themselves. So therefore, if we're in case 1, we would be done because this is a contradiction. Okay, any questions so far? So then suppose we're in case 2, which is that at least half of the sets intersect S in this rather large way. So on at least log m vertices. Well, now we'll finally apply the fact that F has bounded VC dimension. So by Sauer's law, the number of distinct intersections that these sets will have with S will be at most S to the D, which means that there must be one of those subsets, S prime, of size at least log m, such that at least this many sets from my set system intersects S on exactly S prime. And S prime is large. It has size at least log m. And now I can follow the argument of Erdos-Rado by just modifying those sets by pulling all of those log m vertices out to get these sets of size m minus log m. Apply induction to argue that the size of this family is at most this quantity here. And then when you cross multiply this 2SD, you get that the size of the family is at most this FD of m quantity, which is a contradiction because we assume that it was bigger than the FD of m quantity. So that's the end of this sketch proof. Any questions? Okay, so it looks like I'm at the 50 mark, which is good because this is my last slide. So this is what we just proved. We proved this upper bound on this sunflower problem under this extra condition that F has bounded VC dimension setting. One question that we weren't able to solve was actually we couldn't improve this upper bound in the semi-algebraic setting. So we do have some results about certain set systems defined in the plane, for example, like points and disks, but in general, we weren't able to improve this upper bound for the general semi-algebraic setting. So for example, if you have a set system defined by points and spheres in R3, we weren't able to improve this upper bound here. We also weren't able to improve this upper bound if instead of looking for 3 sunflowers, we were interested in finding 3 sets that pairwise intersect with the same size. So that monochromatic triangle I talked about earlier, which we thought was an interesting problem. And then finally, one last question that I like to mention, which goes back to that multicolor Ramsey number stuff. We don't know if we can prove that Schur-Erdos conjecture if we just assume each color class had bounded VC dimension. So remember, if each color class had bounded VC dimension, when you take the union of all those neighborhoods, it's possible that the neighborhood set system has large VC dimension because there are so many colors. So unfortunately, in that situation, our proof breaks down. So we thought that this here would be a kind of a nice next step here. Okay, and so that's it.
Okay, Thanks a lot for a wonderful talk. Let's unmute ourselves and give a round of applause to Andrew. So I see there are questions. Marco asks, is there any intuitive examples of graphs with non-constant VC dimension? Example, graph with n vertices with VC dimension log n or even square root n.
So where's, oh, here's the chat. Okay, sorry. I was trying to figure out the Zoom thing. Are there any intuitive examples of graphs with non-constant VC dimension? Large VC dimension? I mean, in general, like most graphs have large VC dimension. Like a random graph would have large VC dimension. I don't know if a random graph is intuitive. That sunflower bound is surely not the answer. Now that you know it's 2 to the, do you think the truth is? Oh, sorry, this was a different question. So I don't know if the VC dimension intuitive graph answers your question, but most graphs, you know, a random graph, most graphs have large VC dimension.
I mean, if you have n vertices, then the VC dimension is at most log n, isn't it?
Yeah, just because there's, yeah, you can't shatter such a large family. That's true. Okay, so I'll just scroll down to the next question, I guess. That sunflower bound is surely not the answer. Now that you know it's 2 to the little o m log m, what do you think the truth is? I mean, I believe the Erdos-Rado conjecture. So in general, I think the general problem should be 2 to the m. Yeah, log star is a weird thing. So definitely in the bounded VC dimension, I would think 2 to the m is definitely the answer. What about R uniform hypergraphs rather than graphs? Is there, oh, hold on. I lost the, what about R uniform hypergraphs rather than graphs? Is there a good notion of VC dimension that makes some hard problems more tractable?
Right, so for example, just like hypergraph Ramsey problems.
Mm-hmm. Yeah. So, I mean, in general, for many hypergraph Ramsey problems, they're typically reduced to lower uniformities. So if you have like a result about graphs, if you have a Ramsey result for graphs with bounded VC dimension, then if you, so for example, if you have a 3 uniform set system, and then you look at, for every pair, you look at that neighborhood, and then if that's how you want to define VC dimension of a triple set system, by looking at all pairs and then looking at those neighborhoods. Yeah, and then if you want to establish like a Ramsey type result for those triples that has bounded VC dimension, I think the usual technique is to use this Erdos-Rado reduction argument where you kind of lose one exponential and reduce it to a graph. So actually, we were able to show that if your graph has bounded VC dimension, then it contains a rather large Clique independent set. And so therefore, if you want to look at triples, and if you again assume bounded VC dimension and you want to find a large Clique independent set, you can do much better than log n by just reducing it to a graph with bounded VC dimension. You lose one exponential, but then you only pay one exponential to reduce it to a graph with bounded VC dimension. And there you can find a Clique independent set close to polynomial.
Oh, okay. Thanks.
Mhm.
Actually, there's one more thing I was wondering about, because there you're looking at VC dimension via basically the codegree, right? You take a pairs and
Yeah,
look at
yeah,
their
yeah.
neighborhoods. But I guess you could also look at vertices and look at the edges. So does that make a difference for hypergraphs?
Yeah, so
two
it
obvious
was
generalizations,
confusing.
right?
For if you have a hypergraph, then what is the VC dimension? Is it the edge themselves, or if it's the degree? Yeah, we weren't sure what the more natural thing is. I mean, we just started with graphs, and there it was more natural to look at the degree, especially since we came from a geometric point of view. We were trying to answer some geometric questions where that was a little bit more natural. But yeah, it's a little confusing if you have K uniform set system, what the VC dimension is it the degree or the actual sets? I'm not sure which one is the more natural thing to consider.
Thanks for a lovely talk.
Uh-huh.
There's another question by Abrar.
Let me see. Does the sunflower conjecture imply the sure Erdos conjecture or vice versa? Well, so I don't think so. So instead of a sunflower, if you're looking at three sets that just pairwise intersect the same size, which is often called a weak delta system. So obviously the sure Erdos conjecture would imply the, I guess, weak delta system conjecture. Other than that kind of trivial reduction that I mentioned kind of in the middle of my talk, I don't know any other implication. I guess on the surface, the sunflower conjecture seems more doable, I guess, than the sure Erdos conjecture, because it's a stronger thing.
I have a question as well. I was wondering about what is the problem? So you said that your proof doesn't work if the intersection is larger. That seems a bit strange.
So I'm sorry, the proof doesn't work if the intersection.
If you have like larger intersections.
So which one, the sunflower one?
Yeah.
Uh-huh. The proof doesn't work if you have larger.
Like it's your second open problem. If you go there, maybe.
If we just want three pairwise, we just want three sets that pairwise intersect the same size.
Yeah.
We weren't able to really, yeah. I mean, we didn't really, other than induction and kind of following the Erdos-Rado argument of finding many vertices that contain many vertices that lie inside many sets. Yeah, unfortunately, we didn't, our argument didn't say anything about pairs and how they behave. So yeah, I agree. Our proof was, yeah, either induction or many sets have many points in common, and then you imply, you follow the Erdos-Rado thing. Yeah, I'm not sure what else to do.
Any more questions?
I had a question about the multicolor Ramsey stuff. So with this partitioning lemma, where you get to, each set, if it contains an edge of a color, then all the vertices have low degree in that color. Can you boost this to an actual stability result? Like, this is very similar to what would happen in a product coloring. So could you say that actually any bounded VC dimension coloring on exponentially many vertices really has to look like a product coloring, or are these results too weak for some sort of stability?
So I don't know. I'm not sure. I'm not sure. So can you repeat the question?
I mean, there's, you could think the only lower bounds that I can think of are these iterated product colorings. And this sort of seems like you're identifying some structure along those lines. And I was wondering if actually you could actually turn this into a real stability result that actually,
So
if
what do
you
you
have
mean
a coloring
exactly
of,
by stability result?
so somehow that really such a coloring must look like a product coloring in some sense. I don't know what the appropriate thing would be.
Uh-huh. Yeah, I don't think I can give you a good answer that would make you satisfied.
Okay.
Sorry.
No, that's fine. Thank you.
Any more questions? Okay, then let's thank Andrew again, and thanks a lot. I'll stop recording.